In the last video, we drew some pretty pictures of triangles and squares. In this video, we're going to look at some pretty pictures too. Or actually what we're going to do is we're going to look at some of the math or a very simple function. It's not math, it's a very simple function behind a pretty picture. There's this thing called the Collatz conjecture. And it's about a sequence of numbers that work like this. If the current number is even, then the next number is n over 2. If the current number is odd, then the next number is 3n plus 1. And what I've done here is, using the recipe for generative recursion, I designed a ISL function for hailstones. That's what this sequence is historically called. Which basically says, look, when we get to 1, we stop. So if n is 1, we produce the list 1. Otherwise, we cons n onto the next call, which is if n is even, we call ourselves recursively with n over 2. And if n is not even, in other words, if n is odd, we call ourselves recursively with plus 1 and n times 3, which is exactly this rule up here. So there's hailstones. And the reason it's called hailstones is that if you compute the sequence for a number of values, I'll just do it for 10 now. If you compute the sequence for a number of different starting values, and then you measure the length of the sequence, and you plot that, you get a picture kind of like that. But let's talk about something else for a second. Look at hailstones. Hailstones is a recursive function that calls itself with either n divided by 2 or n times 3 plus 1. Let's compare hailstones to the Sierpinski's triangle function. S_tri, the Sierpinski triangle function, is a recursive function that calls itself recursively with s over 2. Now, if you think back a bit, when you first saw recursive functions, I think you probably got a bit concerned. Hey, is this ever going to stop? This function is calling itself. Why will it stop? And then I convinced you not to worry about that, because we talked about the notion of a well-formed self-referential type comment that had a base case and a self-reference case, and how the existence of the base case meant that recursive functions operating on this kind of data would always stop. And the reason they would always stop is that if it wasn't the base case, they were going to take a subpiece of the current data. And by taking subpieces of the current data, in the case of lists, by taking the rest of the list each time, they would eventually reach the base case. Again, in the case of lists, empty. And so that's why we were happy with those recursive functions. We knew they would stop. What about these recursive functions? They're not operating on a well-formed self-referential data definition. So that previous proof that they would stop doesn't apply anymore. What we need for these functions is a 3-part termination argument. Let me show you what I mean. I'm still in termination starter, and the problem here is to do a 3-part termination argument for S_tri. Okay? Now, what I'm going to do actually is I'm going to pick this up and take it over to fractals v1. I want to put the termination argument right there. I'll paste it in right here to fractals v1, and I'll get rid of just the description of it. I'll put just that part. So now this is going to be the 3-part termination argument. The first part of a termination argument is the base case. When does the function stop? You can usually pick these right out of the definition of the function. It stops there. The next part of the argument is the reduction step. What is the argument to the function in the recursive call? What is the thing which the template calls the next problem? Well, again, that's usually pretty easy to pick out of the function definition. In this case, it's s over 2. And then there's the argument that repeated application of the reduction step will eventually reach the base case. What that means is that if I start with a legal S and I keep doing the reduction step over and over again, I'll get to the cutoff. And in this case, that's fairly straightforward. As long as the cutoff is greater than 0 and S starts greater than or equal to 0, repeated division by 2 will eventually be less than the cutoff. I promised we wouldn't do much math in this course. I'm still keeping my promise, but I'm getting a little bit close to it. But I think that even people who don't love math will agree that if you keep dividing a number by 2 over and over and over again, that number is eventually going to get right up to and approaching 0. And so as long as the cutoff is bigger than 0, you'll eventually get to be less than the cutoff. The point of a three-part termination argument isn't to talk about how fast you're going to get there. It's just to prove that you will eventually get there. So with this three-part termination argument, which you should always include when you use generative recursion, we now know that stry will stop. Let's do another one. And this one is so simple that you might find it too simple, but I want to do it because as soon as I do this one, then I'm going to do a trickier one. I'm going to go back to fractals v1, and I'm going to do the three-part termination argument for the carpet. Okay? And in fact, what I'm going to do is let you do the three-part termination argument for the carpet. Okay? So there's the carpet. You want the base case, the reduction step, and the argument that repeated application of the reduction step will eventually reach the base case. This is going to be almost exactly like the one we just did. I'm aware of that, but please do it anyways.